this session, we shall go through some more important problems with main concepts in definite integrals. The very first problem in today's class what are the boundaries of this integral? He has given us certain options. It lies between 2 and e, it lies between 1 and e, it lies between 1 and 2, like that we are supposed to frame. Okay, look here. This integral has been designed between 0 to 1. That is 0 less than or equal to x less than or equal to 1. Multiply with x, 0 less than or equal to x square less than or equal to x. That is 0 greater than or equal to minus x square greater than or equal to minus x. That is e power 0 greater than or equal to e power minus x square greater than or equal to e power minus x. You see, e power 0 is 1. Add 1 on all the sides, 1 plus e power 0 greater than or equal to 1 plus e power minus x square greater than or equal to 1 plus e power minus x. What is e power 0? 1. 1 plus 1? 2. Well, one plus e power minus x less than or equal to 1 plus e power minus x square less than or equal to 2. And we know that e power minus x and e power minus x square are all continuous and derivable in the closed interval 0 to 1 and open interval 0 to 1 respectively. Basing on a particular mean value theorem in integral calculus, we have integral 0 to 1, 1 plus e power minus x dx less than or equal to I less than or equal to integral 0 to 1 2 dx. I mean to say this is I. We could have taken this integral to be some I. Okay, what is this integral? 1. Integral of 1 is x plus e power minus x by minus 1 between the limits 0 to 1 less than or equal to I less than or equal to 2 into integral 0 to 1 of 1 dx is x between the limits 0 to 1. Come on, tell me. If you put x as 1, 1 plus e power minus 1 by minus 1 minus 0 minus e power minus 0 less than or equal to I less than or equal to 2. Okay then, e power minus 0 is e power 0, that is 1, minus of minus 1 is 1, 2, and this is minus 1 by e less than or equal to I less than or equal to 2. So what are the boundaries of this integral value? 2 minus 1 by e less than or equal to I less than or equal to 2. So it lies between 2 minus 1 by e and 2. That's all the answer. The next problem, integral 0 to pi log of 1 plus cos theta. Let me call this I. Now let us make use of the formula. Integral 0 to a f of x dx is equal to integral 0 to a f of a minus x dx, that is x can be replaced by a minus x. Of course, in the present problem we can write pi minus theta in the place of theta. What happens? Let us see. Integral 0 to pi log of 1 plus cos of pi minus theta is minus cos theta d theta. This is I. Well done. Let us add these two. What happens? I plus I is equal to integral 0 to pi log of 1 plus cos theta plus log of 1 minus cos theta d theta. Now log of 1 plus cos theta plus log of 1 minus cos theta, that is log m plus log n is log mn. So it is log of 1 plus cos theta into 1 minus cos theta, that is 2y is equal to integral 0 to pi log of 1 minus cos square theta is nothing but 0 to pi log of sin square theta. Log of sin square theta, that is equal to 2 into integral 0 to pi log of sin theta. This is of course 2i is equal to. Now we can cancel 2. So what is the shape of I? I is equal to integral 0 to pi log of sin theta d theta. Okay, let me consider this pi as some 2a. 0 to 2a f of x dx is equal to 0 to 2a f of 2a, 0 to 2a f of, let me recall the formula, integral 0 to 2a f of x dx is equal to 2 into integral 0 to a f of x dx if f of 2a minus x is equal to f of x. A beautiful formula is there with us. Let us now make use of that formula. According to that, it becomes 2 into integral 0 to pi by 2 log sin theta d theta. Isn't it? That is, in the place of 2a, I am imagining pi. What is log sin pi minus theta? Log sin pi minus theta is nothing but sin theta. Hence log sin pi minus theta is nothing but log sin theta. So there will be no change at all. F of 2a minus x is equal to f of x is happening here. Therefore it is 2 into log sin theta d theta. And of course it is a well-known integral whose answer is 2 into minus pi by 2 log 2. Minus pi by 2 log 2. Hence the ultimate answer is minus pi log 2. The next problem is integral 0 to 1 of tan inverse of 2x minus 1 by 1 plus x minus x square. Look here, this is nothing but integral 0 to 1 tan inverse of, you first observe the denominator, 1 plus x into 1 minus x. Now you think of, is it possible to obtain x and 1 minus x in the numerator? Look here, it's very simple, x minus of 1 minus x. Observe it. X minus of minus x is 2x minus 1. Absolutely. As per the numerator, this is presented here. Okay, this looks like tan inverse of a minus b by 1 plus ab, isn't it? So, it is in turn equal to integral 0 to 1 tan inverse x minus tan inverse 1 minus x. Tan inverse 1 minus x. Again, you split into two integrals, integral 0 to 1 tan inverse x minus integral 0 to 1 tan inverse 1 minus x dx. The next step, imagine. See, integral 0 to a f of x dx is nothing but integral 0 to a f of a minus x. So that you can replace x by 1 minus x here. Hence, first integral and the second integral are one and the same, so that these two can be cancelled, leaving you 0. So what is the ultimate answer? 0. So this idea is needed here, so that it can be split into two equal integrals with minus sign in the middle. So that answer will be 0. It's a beautiful problem and simple problem also. The next integral before us is integral 0 to pi cos 2x into log sin x dx. Cos 2x into log sin x dx. You see, if you replace pi minus 6 in the place of x, what happens? Cos of 2 into pi minus x is 2 pi minus 2x. Fourth quadrant, it is cos 2x. And sine of pi minus x is sin x. There will be no change at all. Hence, if you name this as I, this can be taken as integral 0 to pi by 2 cos 2x into log sin x dx. What is the formula that has been used here? The previous formula, that is integral 0 to 2a f of x dx is equal to 2 into integral 0 to a f of x dx. Of course, if f of 2a minus x is equal to f of x. This formula is being encashed here, isn't it? Okay. Now, this is 2 into integral 0 to pi by 2. I am just rearranging them. Log sin x into cos 2x. That is, I am now going to use integration by parts. Following the Euler rule, logarithmic function must be kept in the beginning. Okay, using the integration by parts, come on. F of x into integral g of x, that is log sin x into sin 2x by 2 log sin x into sin 2x by 2 between the limit 0 to pi by 2 minus integral of derivative of f of x. What is the derivative of log sin x? 1 by sin x into cos x. That is cos x by sin x into integral of g of x. What is the integral of cos 2x? Sin 2x by 2 dx. Okay, what happens to this? This is equal to 2 into, if you place pi by 2, sin pi by 2 is 1, log sin pi by 2 is 0, 0 into anything is 0, 0 minus 2 into first part minus 2 into second part. If you can easily observe that this part becomes 0 even if you substitute pi by 2 and 0 also, therefore you forget it. So this is minus 2 into sin 2x by 2. What is that? 2 sin x cos x by 2. 2 and 2 will go away. Sin x and sin x will go away. Cos x into cos x, cos square x. Cos square x between the limits 0 to pi by 2. Cos square x between the limits 0 to pi by 2 is just nothing but pi by 4. So this is minus 2 into pi by 4 is equal to minus pi by 2 becomes the answer. Minus pi by 2 becomes the answer. That's it. The next question. Integral 0 to pi by 2 sin 2x into log sin x dx. Sin 2x into log sin x is just like the previous problem. Now the present problem is sin 2x into tan inverse of sin x dx. How to tackle with that? This is equal to integral 0 to pi by 2 2 sin x cos x into tan inverse of sin x dx. Okay. Let me take sin x is equal to t. Automatically cos x dx becomes dt. Moreover, thinking of the limits, if x is equal to 0, then t is equal to 0. If x is equal to pi by 2, then t is equal to sin pi by 2, that is 1. Hence, I is equal to 2 into integral 0 to pi by 2 becomes integral 0 to 1. Okay, cos x dx is nothing but dt. Hence, it is tan inverse t into t dt. Tan inverse t into t dt. Okay, let us directly use integration by parts so that it is 2 into, come on, tan inverse t into integral of this t square by 2 minus integral of 1 by 1 plus t square into t square by 2 dt. Isn't it? Derivative of f of x is 1 by 1 plus t square, 1 by 1 plus t square into t square by 2 dt. Okay, between the limits 0 to 1. Well, let us split into two parts. The first part becomes 2 into t square by 2 into tan inverse t between the limits 0 to 1 minus integral 0 to 1 t square by 1 plus t square dt. Why? Because this 2 and this 2 can of course be cancelled. Okay, what about the first part? If you put 1 by 2 into tan inverse 1, 1 by 2 into pi by 4, 2 into 1 by 2 into pi by 4 minus 0 minus integral 0 to 1 t square by 1 plus t square. It can be written as 1 minus 1 by 1 plus t square. 1 minus 1 by 1 plus t square dt. It's very simple. 1 plus t square minus 1 is nothing but t square by 1 plus t square. Well, therefore this is 2 and 2 go away, pi by 4 minus t minus tan inverse t between the limits 0 to 1. Isn't it? Integral of 1 is t and integral of 1 by 1 plus t square is tan inverse t. Okay, substitute the limits. If you take t is equal to 1, 1 minus tan inverse 1 is pi by 4, and if you take 0, it is 0. 0 minus tan inverse 0, isn't it? Okay, pi by 4 minus half minus pi by 4 is plus pi by 4. Pi by 4 plus pi by 4 is 2 pi by 4, that is pi by 2. Hence, the ultimate answer is pi by 2 minus 1. It's a good problem. The next problem is integral 0 to pi by 4 root tan x dx. Another beautiful problem is coming to us. Let us now deal with it very carefully. Integral 0 to pi by 4 root tan x dx. Let me name it as some I. Okay, let tan x is equal to t square. What happens? Secant square x dx is equal to 2t dt. 1 plus tan square x dx is equal to 2t dt. Tan x is t square, so tan square x is t power 4. Dx is therefore 2t by 1 plus t power 4 dt. 1 plus t power 4 dt. Well and good. What about the limits? Also, x is equal to 0 implies t square is equal to 0, that is t is equal to 0. X is equal to pi by 4 implies t square is equal to tan pi by 4 is 1, therefore t square is 1, hence t is also 1. Good. What is the shape of I? I is therefore equal to integral 0 to 1. What is root tan x? Root t square. What is dx? 2t by 1 plus t power 4. Hence it is integral 0 to 1 2t square dt by t power 4 plus 1. Again, this is integral 0 to 1 t square plus 1 plus t square minus 1 by t power 4 plus 1. Any problem? The only thing that I have done here is I could have written 2t square as t square plus 1 plus t square minus 1. 1 and 1 will go away, leaving you 2t square, which is required in the numerator to be present there itself. Okay. Again, this can be split into two integrals, namely t square plus 1 by t power 4 plus 1 dt plus integral 0 to 1 t square minus 1 by t power 4 plus 1 dt. Moreover, even this can again be split as, look here, integral 0 to 1 plus 1 by t square by t square plus 1 by t square dt plus integral 0 to 1 minus 1 by t square by t square plus 1 by t square dt. The only thing that I could have done is I could have divided both numerator and denominator with t square. Well, let me call this I1 plus I2. Now, it is the matter to deal with both I1 and I2 separately. Actually, the things are very visible, clearly visible there itself. Why? You can read the answer directly. How? Like this. I1 is equal to integral 0 to 1 d of t minus 1 by t by t minus 1 by t whole square plus 2. You can follow that, isn't it? That is, I could have written t square plus 1 by t square as t minus 1 by t whole square plus 2. So, this looks like 1 by x square plus a square. What is 1 by x square plus a square? 1 by, this is the derivative of this. 1 minus 1 plus 1 by t square is nothing but, isn't it? So, that it is 1 by root 2 tan inverse of t minus 1 by t by root 2 between the limits 0 to 1. Between the limits 0 to 1. Hence, this is equal to 1 by root 2 into tan inverse of, if you take 1, it is 0. 1 minus 1 is 0, tan inverse of 0 by root 2 is 0, hence tan inverse 0 is 0. Minus, if you take 0, that is minus infinity you have, so tan inverse of minus infinity is minus pi by 2, hence this will be pi by 2 root 2. You see, my dear friend, we could have calculated just I1 only. Still there is I2. Well, my dear friend, because of this particular integral, keeping this particular integral in our mind, we will be able to simplify that also by considering t square plus 1 by t square as t plus 1 by t whole square minus 2. Isn't it? Well done. What is I2? I2 is therefore equal to integral 0 to 1. What is t square plus 1 by t square? T minus t plus 1 by t whole square minus 2, and the numerator is d of t plus 1 by t. We can easily see that this looks like 1 by x square minus a square. What is the integral of 1 by x square minus a square? 1 by 2a log mod x minus a by x plus a. According to that, this is 1 by 2 root 2 2a. In the place of a square, we are having 2, isn't it? So, in the place of a, we should have root 2. Log mod t plus 1 by t minus a by a is root 2. T plus 1 by t plus root 2. Of course, between the limit 0 and 1. Between the limit 0 and 1. Multiply with the t on both sides. We have 1 by 2 root 2 into log of t square plus 1 minus t root 2 by t square plus 1 plus t root 2 between the limits 0 and 1. Well, my dear, if you take 1 plus 1, 2, 2 minus root 2 by 2 plus root 2. This is equal to 1 by 2 root 2 into log of 2 minus root 2 by 2 plus root 2. And if you place 0, 0, 0, 1, 0, 0, 1, 1 by 1 is 1, log 1 is 0. That's all. This is the remainder. One thing is true. If you take root 2 common both in numerator and denominator, you will have root 2 minus 1 by root 2 plus 1. And by rationalizing it, it is root 2 minus 1 whole square. That 2 and this 2 will be cancelled. The ultimate answer is 1 by root 2 into log of root 2 minus 1. Isn't it? I think you could have followed it. Multiply, see, you get root 2 out in the numerator and denominator. It becomes root 2 minus 1 by root 2 plus 1. Rationalize the denominator so that the numerator becomes root 2 minus 1 whole square. That whole square, 2 and this 2 will be cancelled. Ultimately, this is 1 by root 2 into log of root 2 minus 1. This is I2 and that is I1. If you add these two, you will be going to get the ultimate answer. That is the right answer. Of course, problem looks bulkier, but every stage we will be able to trace the answer. We will have the vision of the answer directly. You can imagine the answer because they are thrown into the standard models. It's a beautiful problem. The next problem is integral 0 to pi by 2 log of tan x plus cot x. Log of tan x plus cot x. So this is integral 0 to pi by 2. Tan x can be taken as sin x by cos x. Cot x can be taken as cos x by sin x. So that again it is integral 0 to pi by 2 log of LCM is sin x cos x, and in the numerator it is sin square x plus cos square x is 1. Hence integral 0 to pi by 2 log 1 minus log sin x cos x log sin x cos x. You see, log 1 is 0. So you just need not consider that. This is of course 0 minus integral 0 to pi by 2 log sin x plus log cos x dx minus integral 0 to pi by 2 log sin x minus integral 0 to pi by 2 log cos x. Well, my dear, you can observe that these two integrals values are numerically equal because if you replace x by pi by 2 minus x, this becomes log sin x. Log sin x, log sin x. They are numerically equal. Hence, this can be written as minus 2 into integral 0 to pi by 2 log sin x. And we know that integral 0 to pi by 2 log sin x is nothing but minus pi by 2 log 2. So that it is pi log 2. So the answer is pi log 2. The next problem is integral 0 to pi by 2 dx by root sin x plus root cos x whole power 4. Root sin x plus root cos x whole power 4. Well, I like to simplify this. You please follow the steps which I am following. Dx by root cos x into root tan x plus 1 whole to the power of 4. Am I correct? I have dragged root cos x out so that it is root tan x plus 1. And you see, root cos x whole power 4, what is that? Cos square x. If it goes to the numerator, is nothing but integral 0 to pi by 2 secant square x dx by root tan x plus 1 whole to the power of 4. This is your I. Now, everything is very, very clear before us. Take tan x is equal to t. Let tan x is equal to t. Implies secant square x dx is therefore equal to dt. What about the limits? X equal to 0 implies t is equal to tan 0. X is equal to pi by 2 implies t is equal to tan pi by 2, that is infinity. Okay, friend. What happens to the nature of I? I is then integral 0 to infinity. What is secant square x dx? It is dt by root t plus 1 whole to the power of 4. Again, how to play with that root 2 plus 1? Look here, let root 2 plus 1 is equal to u. Implies root t is equal to u minus 1. Implies t is equal to u minus 1 whole square. Implies dt is equal to 2 into u minus 1 du. Am I right? U. Okay, let us see about the limits. What happens if t is equal to 0? T is equal to 0 implies root t is equal to 0, u minus 1 is 0, u is equal to 1. And if t is infinity, automatically u is also infinity. U is also infinity. Well, with this new substitution, what is the fate of I? I is therefore equal to integral 1 to infinity. Come on, instead of dt, you are supposed to write 2 into u minus 1 du. By, instead of root t plus 1, you are supposed to have u power 4. And of course, it is very easy to simplify. 2 into integral of u by u power 4 is 1 by u cube minus 1 by u power 4 du between the limits 1 to infinity. 1 to infinity. Well done. What is the integral of 1 by u cube? Minus 1 by 2 u square minus 1 by 3 u cube between the limits 0 to infinity. That is 2 into 1 by 3 u cube minus 1 by 2 u square between the limits 0 to infinity. If you put infinity, it becomes 0, 1 by infinity 0, 1 by infinity 0. Therefore, this is 2 into 0 minus, come on, take 1 in the place of u. 1 by 3 minus 1 by 2. What is 1 by 3 minus 1 by 2? Minus 1 by 6. Minus of minus 1 by 6 plus 1 by 6. 2 into 1 by 6, 1 by 3. We shall now look at the problem which is available on the board. You follow it carefully. 0 to sine square x of sine inverse root t dd plus integral 0 to cos square x of cos inverse root t dt. Well, let me call this I, and I like to suppose this is I1 plus I2. Let us consider this the sum of two integrals as y1 plus I2. For I1, let root t is equal to sine u plus t is equal to sine square u dt is equal to 2 sin u into cos u, that is sin 2u du. Moreover, what about the limits? If t is equal to 0, sin u is equal to 0, then u is equal to 0. If t is equal to sin square x, then sin square u is equal to sin square x, then u is equal to x. U is equal to x. Similarly, for I2, now you take root t is equal to cos theta, t is equal to cos square theta d theta, cos square theta, dt is equal to 2 cos theta into minus sin theta, that is minus sin 2 theta d theta. Moreover, about the limits, t is equal to 0 implies cos square theta is equal to 0, cos theta is equal to 0, theta is equal to pi by 2. T is equal to cos square x implies cos square theta is equal to cos square x, so theta is equal to x. Well, keeping these points in view, let us now look at I. I is therefore equal to, first of all, instead of 0 to sin square x, we should have 0 to x. 0 to x, sin inverse of root t, that is u. What is dt? Sin 2u du. Sin 2u du. Plus, for I2, what happens? Instead of 0 to cos square x, we have to write pi by 2 to x. Pi by 2 to x, cos inverse root t, cos inverse of cos theta, that is theta, dt minus sin 2 theta d theta. Well, we could have estimated this. Now, this is the time for us to simplify it. Well, I like to remove these steps so as to save some space. Follow it carefully. Therefore, I is equal to integral 0 to x u sin 2u du plus integral x to pi by 2 theta sin 2 theta d theta. I think you could have observed what I have done. Here, this minus symbol is being utilized to change the limits from pi by 2 to x to pi by 2. Now you observe 0 to x and x to pi by 2. Same function. Hence, this is integral 0 to pi by 2 u sin 2u du. You can write like it. Why? Because instead of theta to theta sin 2 theta d theta, why can't you write x to pi by 2 u sin 2u du? U sin 2u, u sin 2u. One is 0 to x, another is x to pi by 2. Total 0 to pi by 2 u sin 2u du. Now, it is very simple and direct, of course, to simplify this. U sin 2u, of course, by using integration by parts. How? This is equal to u into minus cos 2u by 2 between the limit 0 to pi by 2 minus integral of derivative of u is 1 minus cos 2u by 2. This is equal to, look here, 2 into pi by 2 is 90. 2 into 90 is 180. Cos 180 is minus 1. Minus of minus 1 is 1. 1 by 2 into pi by 2. Isn't it? Pi by 2 into 1 by 2. Minus, if you take 0, it will be 0. Plus 1 by 2 into integral 0 to pi by 2 cos 2u du. Cos 2u du is equal to pi by 4 minus 1 by 2 into, what is integral of cos 2u? What is cos 2u? Sin 2u by 2 between the limit 0 to pi by 2. Between the limit 0 to pi by 2. isn't it? Okay. This is therefore pi by 4 minus 1 by 4 into, if you put pi by 2, 2 into pi by 2 is 180. Sin 180 is 0. If you put 0, it is automatically 0. Hence the ultimate answer is pi by 4. Is pi by 4. If follow it carefully. It's a beautiful problem. So the main idea to solve the problem is the transformation, sin inverse root t and cos inverse root t, and the limits are conveniently brought to 0 to pi by 2, so that a numeral answer is going to be obtained. Answer is pi by 4. The next problem is integral ln2 to x dt by root of u power t minus 1 is equal to pi by 6. Then x is equal to. Let e power t minus 1 is equal to u square. E power t is equal to u square plus 1. E power t dt is equal to 2u du. You see, what is e power t? U square plus 1 dt is equal to 2u du. That is, dt is equal to 2u du by u square plus 1. Plus 1. Well, LHS is equal to this integral. Now let us change the limits also. You have introduced a new variable u, of course. If t is equal to log 2, t is equal to log 2 to the base e power t is, what is e power t? It is 2, isn't it? Implies u square is equal to 2 minus 1, therefore u is equal to 1. Well, if t is equal to x, then u square is equal to e power x minus 1, so u is equal to root of e power x minus 1. Okay, what is LHS? Integral ln2 to x. Instead of that, we write integral 1 to root of e power x minus 1. Of what is dt? 2u du by u square plus 1 into root of e power t minus 1 u is u. U and u will be cancelled, of course, so that is 2 into tan inverse u between the limits 1 to root of e power x minus 1. Isn't it? So this is 2 into tan inverse root of e power x minus 1 minus tan inverse 1. Okay. Tan inverse root of e power x minus 1 minus tan inverse 1. But RHS is pi by 6. Therefore, tan inverse of root of e power x minus 1 minus pi by 4 is equal to pi by 12. Pi by 12. Therefore, tan inverse of root e power x minus 1 is equal to pi by 12 plus pi by 4. What is the LCM? 12. Pi plus 3 pi, 4 pi by 12. 4 pi by 12 is pi by 3. Pi by 3. Tan inverse root of e power x minus 1 is pi by 3. Therefore, root e power x minus 1 is equal to tan pi by 3 is nothing but root 3. Root 3 implies e power x minus 1 is equal to 3, or e power x is equal to 4. E power x is equal to 4, or x is equal to log 4 to the base e. X is equal to log 4 to the base e. That is the answer. Please follow it. It's a good problem. You see, this is 2 into is equal to pi by 6. So this is equal to pi by 12.